Section 7.5 is called the capacitor and reactive power. We're going to take our simple circuit that we had in section 7.4 of the inductor, and now we're going to add a capacitor in parallel with it. They'll both see the same voltage, the same level of that voltage, and we're going to explore what simply adding this capacitor to this circuit did, and I'll hold off on giving you any real practical applications for this until later, but I will tell you this. One thing that's very common in motor applications is the simple addition of a capacitor in parallel to that motor. And the reason for that is that it is a source of reactive power, and it helps correct this thing that we're going to study in section 7.7 about power factor. Let's look at a circuit now with the capacitor added. Here's our circuit. Looks just like the other one, except now we have added a capacitor to the circuit. So here is this capacitor element that is added in parallel to the inductive element. And as you can see from this, that capacitor is seeing 120 volts. And here's our inductor in here, and it's still seeing its 120 volts. And so, you know, that's the only change that we've done to the circuit. We simply added a capacitor. And we're going to make this simple and easier to understand by giving the capacitive reactance equal to the inductive reactance. So we see that the capacitor is minus 4J and the inductor is plus 4J. A couple of things I'll point out to you is, you know, in parallel, this 4J or 4 ohms of inductive reactance is still going to draw 30 amps. And the capacitive reactance is at 4, and it's also going to draw 30 amps. But something is going on here to where it says that the current drawn by this circuit is 0. Okay, so you know, as we go through this, we see the things going on, and it's sometimes, you know, good to have 2 representations of this. And we know that in an inductive circuit, that the current lags the voltage by 90 degrees. We're seeing that. And in a capacitive circuit, the current leads the voltage by 90 degrees. And we're seeing that represented in this phasor diagram. Now, if I've got 30 amps in this direction and I've got 30 amps in this direction, the net current, these cancel each other out, right? So what you're seeing is the vector sum of I sub L and I sub C is 0. So the AC generator is no longer supplying any power at all to the circuit. You say, how can that be? Well, power is voltage times current. So if current is 0, the power being supplied is going to be 0. All right, but however, the current in the reactor has not changed. So how can this be? How could this be? Where is this reactive power coming from? If it's not coming from here, it's got to be coming from somewhere. And of course, the answer is the reactive power is coming from the capacitor. It can only come from the capacitor. It is the source of the reactive power. The reactive power delivered by the capacitor is equal to the current it carries times the voltage across its terminals. And so it is 120 volts times 30 amps. And it's going to be 3,600 VAR, volt amp reactive, or 3.6 kVAR. The reactive power delivered by the capacitors expressed in kilovar or VAR. Reactive power Q now flows from the capacitor to the reactor. Flows from the capacitor to the reactor. So we come to this new conclusion that a capacitor acts as a source of reactive power. Again, I want you to know something here. This is not some theoretical kind of thing to make everything work. This actually is occurring in this circuit. Okay, so we take it a little bit further now. Okay, so we had this situation here. Now we take it a little bit further and we take the inductor out of the circuit, and this gives us this figure 7.8a, and the capacitor is now alone, connected to the terminals of this AC generator. It still carries a current of it's still the same generated value, 120 volts. So it's still carrying the 30 amps of current like before, and it is leading the voltage by 90 degrees. The capacitor still acts as a source of reactive power, but where does this power go? Okay, so the power flow diagram shows reactive power Q flowing back to the source. The answer is the capacitor delivers reactive power to the very generator that it is connected to. If we had a VAR meter connected to this circuit, it would look like this, where the power is flowing back to the generator. The needle would reflect in that direction. And so this is going on in the circuit. For most people, me included, it takes a little time to accept that this could be occurring. How can a passive device like a capacitor, produce any power? The answer is, like reactive power that represents energy that flows back and forth like a pendulum without ever doing any useful work, the capacitor acts like a temporary energy storing device, and instead of storing its energy in a magnetic field, it stores energy in an electric field. And we studied about that when we looked at capacitor action. So there's this electric field here that is energized. And so, or sometimes they call that electrostatic energy. And so, connecting to a voltmeter, we would get a negative 3600 VAR reading from this circuit. The generator is now behaving like a reactive load because it is receiving the power. So the generator now is a reactive load. The source is the capacitor. Okay, and we need to have these definitions going forward. So we prefer sometimes to call it a receiver, the generator's receiver of active power. And in summary, a capacitive reactance always generates reactive power. A capacitive reactance always generates reactive power. Now, what we're going to do next is take this to another level. And let's see, how far along are we here? Let's, I tell you what, we'll make, we'll just finish it. Let's just finish this section here. Example 7.3. I've got an AC generator, and this looks kind of complicated. This looks like one of those problems we might have to do mesh or nodal analysis on. Ugh, but you're going to see we don't. All right, so we have an AC generator here. It's connected to a group of resistors. Got two resistors. We got an inductor, and we got a capacitor. Okay, and we've got all of that there. If I wanted to summarize this, and the total of this would be 2 plus 4 is 6, and this would be plus or minus j, x of L minus x of C, 6, and this is 3.5, and this is 3, so this would be 6 minus j 0.5, in rectangular form. All right, do we even need that? I can't remember. I don't think we do. But anyway, that's going back to circuit analysis stuff. All right, so that's what we have. there. And so he says, calculate the active and reactive power associated with the generator. Now, the neat thing about power calculations, and it makes these things so much easier, is that all we have to do here is we look at our two resistors. Now, since this resistor has the current and resistance already there, we can calculate the power in this first resistor, this 2 ohm. The power is I squared times R. And we know that that's going to be given to us as 16.12 squared times 2. But there's also another resistor out here, and it's seeing 14 amps. So the power from this resistor is I squared R, okay? And that's going to be 14 squared times 4. And so the two powers together is the total active power that is associated with the circuit. So I have 784 watts here, since it's active power, and I have 520 watts here. So the total active power in this circuit is 784 plus 520, which would be 1,304 watts. The 3 ohm reactor here absorbs reactive power, right? We know that from definition, and that is represented by Q sub L for reactive inductive element, reactive power represented by Q. We know the current, and then we multiply that by the inductive reactance. So I get 14 squared times 3, which is 588 var for the inductor. Now I go to the capacitor, and luckily we didn't have to do any determination of what that current was, because we remember that was a little bit different, right? Thinking about how to work that out. But anyway, so we don't have to do that. All we need to know is that for this, it's going to be reactive, Q sub C, and it's going to be 20 squared at the current times 3.5 for the capacitive reactance, and that comes out to be 1,400 var. Okay, and so the total RLC circuit generates a net reactive power of 1,400 var minus 588 var, 1,400 minus 588, and that equals 812 var. Now, since the capacitive portion of this was larger than the inductive part, then this is primarily a capacitive circuit. The reactive power must be absorbed by the generator. As far as reactive power is concerned, the generator acts as a load of reactive power. The active power absorbed by the resistors must be supplied by the generator, and it is that much there. So here is this generator, and it's doing two things. It's a source, this thing, it's a source of active power of 1,304 watts, and it's a receiver of reactive power in the amount of the difference between 1,400 and 588, or 812 var. Okay? Now, hold on to that. I know that, that's a little bit strange and all brand new to you, but, just try to understand what we did. Notice we didn't have to trace currents. We didn't have to determine polarities. All that was given to us, and all we had to do was determine the active power component and the reactive power component, and we were able to make all these determinations with this particular circuit.